Okay, this was short. Thank you very much. So, first of all, I would like to thank especially Jan Klinger and the organizers. This is an excellent meeting, a very beautiful meeting. Also, it's a sad cause, of course, to bring you all here together. And I would also like to extend my thanks to the excellent team behind it, because catering is superb, and it's really what we can learn from. Okay, the next, what I would like also, Jan, which was really marvelous, is that you have 20-minute talks and 10 minutes of discussion, which is also great. And I see that this is opening more, and probably also for future things. The next thing, before I start, is there is two words, intraplate and deformation, in my title. Here's my email. We are just currently preparing a special volume on intraplate tectonics and deformation, also of low seismic areas, of course. If you're interested to contribute, deadline Christmas, more or less. We will send around more information soon. I will distribute it via Jan over this mailing list of this meeting, and so we continue. So, of course, it's not my own work, and I have a lot of co-authors, and this is the PhD students and the Geological Survey, and Stefan, who is always a good guide in intraplate tectonics. And as you can see, the last word is Germany, and this is how I will end with some German disgusting, let's say, summary at the end of the talk. Okay, so why are we going to do these studies? First of all, this area is a silent area. This is a low deformation area. We have seen faults today which make like 10 millimeters a year or even more. These faults are 100 times slower or even more slower. So all your methods, very nicely shown by Dean, Star and others, they need a lot of more time to evolve. So what we are working on, this is the so-called ECRIS, the European Central Rift System. Here you can see the Bressgraben, a strange zone of transfer to the Upper Rhine-Graben, which I will not talk today. And I learned that Fessenheim is in France from Jan, which is situated here. We will concentrate on this piece, the Lower Rhine-Graben in the north. So these are the slip rates, rather small slip rates, and my word silent here refers to either no seismicity or seismogenic faulting, scarce geomorphic and geologic visibility of these faults. So this is really a riddle we have to work on. This is the seismic map of Germany. You wonder why we have this bulby shape here. This is because this map was generated during a nuclear power plant project, because Germany changed regulations for nuclear power plant after the Hochwalking, and we needed to have like 100, 200, and 300 kilometer radius around these nuclear power plant, and this is why the map was generated. So you see some faults, of course, the Alps here, then the Upper Rhine-Graben with the Hohenzollern-Graben, so south of Stuttgart, then the Lower Rhine-Graben here, then you have the area in between Czech Republic and Germany, so this is mainly volcanic activity and swarm activity. Then you have the Lorraine area here, which is, of course, induced earthquakes, like the coal mining in the Ruhr area, the salt mining here, and some other, which are more or less hydrocarbon extraction earthquakes, so anthropogenic things. However, you see Kremer et al. Studying the area of the Eifel, they also put the Lower Rhine-Graben with a high earthquake density. What are the causes for these earthquakes? So, to make it simple, there's 4 causes. First of all, there is the mid-Atlantic ridge push. The Atlantic is an old guy like me, and forces are not that strong, but still we can measure them. Second are the Alps. Also, you know, the Alps are more than 20 million years old. Also, these forces are not the largest one, but this is still quite active. Then we have a third one. This is the glaciation and glaciation from the ice ages. You have to remember, more or less somewhere here was the ice in Salien, so 200,000 years ago. So we were covered. All this was ice covered. And lastly, the Eifel plume, and you see this is, of course, a volcanic hot area. and there may be uplift and other things surrounded by these things. So these are the forces we are fighting with in our area. Presently, sigma H. Max is directly like 150 degrees, so inducing in the upper Rheingraben here, which is the Triassic part in Central Europe, in a sinistral, let's say, graben system, and in the area of I'm talking today, more or less like pure normal faulting in this area. If you look at the opening of these lower Rheingrabens, you see it's not really related to that one because the pivot, the rotation point is here near Karlsruhe and it's opening this way. So it must be maybe something coming from the North Sea inducing this ground. So this is the area now for you for orientation. Here is Bonn, Cologne, Aachen, and you see there's a set of parallel faults all longer than 50 kilometers here, and seismicity in orange, the historical seismicity, in red, the actual one, the instrumental one, is concentrated more or less in the west part. So Cologne and Düsseldorf and Gladbach and these areas, not really, but this is the concentration of it. There's really a low to moderate seismicity. We have damaging historical earthquakes. It is densely populated, more than 6 million people, and there's critical infrastructure, as you may know, the aspirin. This is exactly produced here in Leverkusen, a little bit north of Cologne, so there's big chemical industry along the Rhine. These faults are like 50 kilometers long or longer, and this suggests, following the Wilson-Kuppersmith relationships, more or less like a magnitude 7. And we have a guy here sitting in the front row who has excavated like 25 years ago a magnitude 7 earthquake in the Belgium, Netherlands area where the faults are more or less trending to. So what is the problem? In principle, these faults behave really strange. This means we need to trench all these faults and to see what happens at segment boundaries. What is here in these bridges? Why do we have these aseismic areas and so forth? There's a lot. And the next important question is, it's white down here because this is not already Rhineland-Palatine, so another country in Germany. And you see, this is where the faults end, and I would like to show you that in this slide. So coming down, so again, here is Cologne, so the faults are coming down more or less along the same strike. Here is Lacher See, 13,000 years ago, big eruption, and you see the faults end somewhere here near the Moselle or Mosel River near Koblenz. You see here, oh, it's not normal anymore, so it's like a sinistral component pointing to the area of extension. So if we look at the depth of the earthquakes here in different colors, you can see around the volcanoes, we have these kind of greenish, yellowish earthquakes. Then we have like here along the fault zone, some which we expect normal, like 15 to 20 kilometer. But if you look at the orange and the yellow ones, these are these. And these earthquakes are deeper than Moho, so maybe one reason to stop the rift down here is because there are fluids and migration of fluids to the top of the crust in the volcanic area. So you can see. So a fault zone you have never heard of, Ochtendung, this is an exit here on the highway, is the most active fault seismically in Germany. And we have here the deepest earthquake in Germany, well below the Moho. Okay, let me go back to the Rheingraben, and you see this is the Rheingraben. So Aachen is situated here. This is the direction Cologne. You can see there's a set of Horst and Graben structures. They dip either west or east. They have like sometimes a little bit of antithetic faults here associated with, and this is active since mid-late tertiary, and this black one is lignite. And I'm coming to this in the second part of my talk, to these lignites. You see, everything is dipping more or less towards Cologne. And the next thing is you see that these faults have been since sedimentary active, so-called growth faults. Here in Aachen area, where we don't have these tertiary deposits, you see, the people are still not clear what it is, because there is tertiary inversion, Cretaceous inversion. So a reverse movement on the fault, and today I observe normal movements, but in the map you will still see this as the reverse fault, okay? So there's still some discussion going on. The fault density is much more complicated and much closer than in the previous map. So again, Cologne, Bonn, Aachen. Here you can see these are these open pit mines for lignite. And of course, there the mapping is really nice. I'm going to show you now some of the examples of these faults. You see, we have like 12 trenches done in the area, and we have only rare Holocene rupturing events. So how we do it? You can see here some kind of models. So you see high groundwater table, low groundwater table, plants don't like that. This not so much, but it may be also reverse. Sometimes the fault is covered by landsliding or solifluction, so we don't really see it. Sometimes we have this kind of spring horizons directly at the fault. And if I show you this image, this is not the taiga, this is not Mongolia, this is Highway A4 from Aachen to Cologne, in the village of Düren, and hopefully you can see quite nicely the fault. Okay, yeah, this is not a mountain range one, but the fault is there, and this was the one, by the way, active 1756 in the Düren earthquake. So, bringing you down to the trenching area close to Aachen, in this area, so the so-called Feldbiss fault, we have to fight other things, and I'm going to also focus this a little bit in my second part, but there is mills from along the river during medieval times, because this is copper area, copper, lead, and zinc area. There's roads, tunnels, and of course bombing, because this was heavily fought in the Second World War. So this is, if you have students, you can see the scarp is here. Oh, there's a willow tree on the fault scarp, which indicates water. Usually, you know, willow trees along creeks, but this is on the mountainside, okay? So very, very nice. So the students do the work for us. Here's the results. You can see the ERT, so the electric resistivity. You can see here are some markers inside. So the fault is running somewhere here. We did, of course, also some shallow vibra coring, and you can see between these four and that one, there's the fault inside, because here sand comes in. So somewhere here should be the fault. And indeed, we found the fault. So I need to hopefully start this one. Yes, here it should. Yeah. Oh, stopped it. Go. So this is done by my iPhone, by the way. You can scan beautifully these trenches today. And you see, we found the fault, of course. Here it is. This is older stuff. I want to show you this brownish layer, which splits up in 1, 2, 3, more or less. And what is that? The farmer waste of the last century. Exactly, by the way, where I suspect to have the Holocene deformation, okay? And you see, my student, he was not really happy, because this is a German rifle, Second World War, which comes out of that. So what did we do? A parallel trench 5 meters apart. And this is showing, so this was the first, this is number 2. Here again, where we are, and you can see this is nicely the fault trace. Marte, who is also here, has mapped it nicely. There are some kind of triangular facets, if you wish. You see this is, of course, you need some imagination and exaggeration of the topographic models. But you see the springs and the creeks and maybe some secondary faults down here. This is quite nicely. So this is this is the trench log without rifles and other waste. You can see quite nicely these layers. This is these solifluction layers. You see it's nicely folded in the hanging wall, sometimes a little thrust because of space and accommodation problems. Here's the major fault zone. Some events produced like display Y-shaped faults, and we did a lot of OSL and radiocarbon dating here. And so I'm not going into detail with this because this is about to be published, but you can then get it. But you can see these horizons and especially the different stratigraphy from hanging wall to foot wall. So what we did is restore it, and starting here, this is the youngest, and this is like event number 4. See, this is the topography, and you can see the throw. You see the throw is like 40 to 70, and then from this time on, it's only like 15, 16 centimeters. And this puzzled us a bit because we are thinking we need to re-establish and rework the older trenches we have made to find if there is really that smaller displacements in which people may have overlooked. So this youngest event is younger than 7th century, but then we have a long time, like 20,000 years, 25,000 years with nothing. We have two which almost overlap in the Löss deposits. And then we have an older one down here. And these ones, there is more, which we have not resolved yet because there is stratigraphic markers missing. So this is the restoration of it. And now I'm going to show you the second part. I promised you this the problem. Ooh. Yeah, this is the open pit mine of lignite. And first of all, this is the stratigraphy as it should be. And this is the tailing. So the people, they put this here and then they get the coal and they refill it. But you see, it's dry. Just to give you an order, this is 110 meters to 100 meters above sea level. And this is minus 300. So this is a 400-meter deep hole, okay? And it's dry. So what does it mean? I put these circles, you can see these are the excavators. They are 100 meters high and 150 meters in length. If there would be one of your Chinese Toyotas, Jerome, you won't see them, right? They are sand grain inside these pit, so they are gone. So it's simply to get a dimension. But what they are doing is they lowering the groundwater table to almost 450 meters, okay? And I'm showing you now the consequences of that. The consequences is that we really, and this is especially for Tim, for you, of course, this is the area in Germany where you get fringes in 5 years observation, okay? So, and without any earthquake deformation. And so just to tell you, here's the open pit mine. No, I have done it better. Look at this. This is the open pit mine. This is another smaller one in the near. This is the Feldbiss fault I showed you just before. This is the Sandgewand where we also trenched already. This is the Ruhrrand fault. I have shown you this part before in the field. I'm going to show you that part a little bit later. And there's the Elft fault, another one. You see, this pumping since 50 years is reactivating these faults. Okay? And still the question is, what are they doing? This is 500 meters, but remember the seismogenic depth is like 15 to 20 kilometers. So this is still a question how we work with this. Okay, so anyway, you can see nice linear features here, and they are lined along this fault, and this is exactly what I have shown you in my sketch before. This water is because the water pumping and the faults, they are hydrologically barriers and active, and this is what you can see here. So there's differential movement along with that. So this is a trench I was called, by the way, in a fire department, they want to construct at the moment, and it was the archaeologist calling me. They only had like this, more or less exposed, and I said, maybe you can go 2 meters deeper, and they did, and you can see beautifully brittle seismogenic faulting down here. You can see 1, 2, 3 of these gravel layers, which are nicely faulted. And then it really gets a bit blurry in the Löss deposits. You already know them from the previous trench. But look at the top layer. This thickness here and this thickness here. And the farmer told me, yes, every year I have to fill it up. Okay. So this is not the fault slip in terms of seismogenic. This is anthropogenic thing. So here's our interpretation. You can see the thickness changes down here. Of course, there is some seismogenic faulting. This is, you can see some ice wedges here. So this is still ice age time. This is post-ice age time. And this is our time, more or less. And so this is disturbing the entire picture. Okay, so bringing you to the fault. The fault is running through this beautiful building, a citadel. And luckily, they have done an Élysée, you would say in French. A high school is down here. And here is the LiDAR image for this beautiful building. This is the school. Notice there is a gap in between, okay? And they have to put it on hydraulic pillars to readjust the building, okay? So this is what's going on. this young man is standing in the German case of the Hayward Fault. Yeah, there's a creep going on, and you can see this is almost 40 centimeters, and they have to reconstruct the tunnel inside the citadel, always with concrete, as you can see here. So there's a lot of these measures. So, sum up, because you're getting nervous. Faults are parallel. They have different lengths. We have equidistant faults, more or less, and blocks. And the question is, there a general behavior? It's reactivated by pumping, and the question is, which is the next fault to move? So earthquake models do not really help in that area. Is there sympathetic movement? This is likely, if, as you have seen, 11 versus 70 centimeters of displacement. And the next question is there earthquake clusters? So do earthquakes occur at a certain time, and then the same fault is shaking repeatedly? So, and for my last image, for sensible persons, please close your eyes now. For the others, enjoy it. Here is the earthquake, okay? This is not Oktoberfest and this is not Carnival, but it's Cologne, close to the area. Look at how the people move, yeah? Because they like the music coming from here. And I think this is more or less a model I will work in future on for my thoughts. Thank you very much for your attention.